Yes, it does. Very good. So think about a setting where you're on a graph, and there's one random individual in the graph who has a particularly juicy rumor. And we're trying to figure out how long it will take the rumor to spread, for example, to you, thinking of you as being a uniform individual in the graph as well. Okay? That's one type of question that you could ask. You could also ask the question how long it will take to the juicy rumor to be heard by everybody in the graph. Right? So there's various problems. Now, how would you want to model this? Well, one thing you could do, and this is certainly the easiest thing to do, and it's related to an old problem in probability theory, which is called first passage percolation, is to assign a certain traversal time to all of the edges. It's basically the amount of time that you need to be able to tell the rumor to any of your friends. And then we're just going to be assuming that all of these traversal times are going to be completely independent and identically distributed. Okay? So now we have a random graph that also somehow has a random metric structure associated to it. So you can think of the distance between two vertices as being, two vertices that are in an edge, or in general two vertices, as being the length of the geodesic that connects them. And it's actually these geodesics that describe the rumor spread. Okay? Now, in general, I will be assuming that these edge weights, so the traversal times, are IID continuous random variables. You know, it takes a bit of time for you to actually encounter one of your friends and to tell the juicy rumor to him or her. If you would be talking about graph distances, then we should be weighing our graphs, all the edges in our graph just by a weight 1 for every edge. So that's not continuous, but it's sort of in the same league. We're sort of making the problem a little bit more continuous. And what I'll be interested in, and this is actually a problem that I've borrowed, or that was told to me by a professor in electrical engineering, who was interested in sort of shortest paths in internet. Now, it's not exactly known what the topological structure of the internet is, nor is it really known how messages traverse the internet. But it's believed that there's some form of shortest weight policy taking place. And this is exemplified by an advice that Cisco gives. So Cisco is the producer of routers in the internet. And it gives the advice to its users, who actually install these routers, that the edge weights should be proportional to the bandwidths of the physical cables that are going into the router. In fact, inversely proportional. Now, of course, we don't know what the distribution is of bandwidth of cables in internet. Some cables are extremely thick, some cables are extremely thin. So I have no idea what it is. So again, I'm going to be assuming that this bandwidth distribution is a continuous random variable, and then also these edge weights are going to be continuous random variables. Now, this is a measurement or a data set that really comes from the internet. And what people do in the internet is they send probe packages from sources to destinations. And of course, they cannot compute the total weight of the path in the smallest weight routing, and it wouldn't even be clear what the interpretation of these weights is. But what they can measure is the amount of hops that they make. Basically, the number of routers that the message goes through. And the reason for this is that there's a measurement that you can do that is called trace route, and that allows you to not only send a message from A to B, for a given A and a given B, but also in the end to be reported precisely the routers that the message has passed through. So not only are you going to see whether the email message has arrived at the right place, you will also see precisely how many hops were made. So if you do this for lots of sources and destinations, and there are actually companies or research centers that do this, you get a plot like this. So this is an image for the number of hops made by email messages between various sources and destinations. And this looks quite a bit different than my small world pictures, which somehow were all bounded by at most something like 10, and you really saw a discrete pattern. This almost looks like a Gaussian, or maybe a Poisson distribution. And the values go all the way up to something like 27. And I think at the time that this was made, there was really a cutoff at 32. Because somehow when the message was going around through more than 32 routers, the system would think, you know, the thing has failed. So it would just be cut, and basically they would try again. Okay? So the fact that you have values relatively close to 32 is maybe a bit alarming, but okay, that's what it is. So what we were trying to do was to understand where this picture comes from and whether you can describe this picture. So bear in mind, if we're assuming that the internet works through shortest weight routing, smallest weight routing, that is not obvious. Then here we're not seeing the actual times for the messages to arrive, but we rather see the number of hops made along the shortest path. So that's a very indirect measurement. Okay? Okay. So this is related to smallest weight routing, and this problem in terms of the rumor spread would be sort of when the rumor actually goes from the starting individual to, let's say, you, how many people has it passed through? So how often has the rumor been retold before it arrives to you? Now, if you've ever done a Chinese game, Chinese whisper game, you will actually know that this is a relevant measure. You know, the more often the story is being told, the more corrupted the story becomes. Or the more juicy the rumor becomes. It depends on your perspective. But certainly there's changes to the story every time the story is being retold. So even in that sense, this measure is a realistic and useful thing. Okay. So smallest weight routing problems are interesting from all sorts of applications, but also they serve as a building block for many other problems that people have been investigating in the literature. Think, for example, of epidemic models. This is the simplest version of an epidemic where you can infect your neighbors, you never recuperate. That's it. Yeah, so this is sometimes called an SI model compared to an SIR model or an SIS model. Or, so it's the simplest model of an epidemic. Of course, a rumor spread, it's actually used in CS quite frequently for all sorts of randomized algorithms, and particularly in terms of sensor networks. So in sensor networks, you have very small devices that have a very limited capacity of memory. And if information comes in, you use the sensor network, it's an ad hoc network, in order to get the information to go to a base station. But then the question is, when there are multiple messages coming in, sort of how long should you keep track of the messages? Which one should you keep? Which one should you throw away? How long does it take the message to arrive at the base station, etc., etc. So again, this is very closely related to the problems that I have here. Now, a final thing that I will say something about later on is a competition process, where now, rather than thinking of a rumor spreading, you take two sources and are trying to compete for territory in the same way as the rumor spreading would work. It's just that when one of the two types grabs a vertex, the other can never invade it. So it really is competition. And then the question is, who gets the majority of the graph? And what are the relative sizes? So who wins? And how much does the losing type get? Okay, so that's a competition process. And we will see that this rumor spreading model is one of the most basic models, and it actually gives us lots of information about some of these other problems as well. So what is in general the setting? We have a graph. And in fact, my graph will typically be a configuration model in this talk, but you could also think of it as being a generalized random graph. We know that these models are very closely related. The number of vertices is n. And sometimes I will also be thinking about the setting where my graph is a complete graph. That's actually also quite an interesting setting. In your sensor network, this would correspond to the fact that all your sensors can talk with one another. Okay? And then we're interested in let's say the weight of the geodesic between two random individuals. You take two random vertices, and you look at the smallest weight path between them, and that's denoted by this Cn. It's the minimum of overall possible paths that go from V1 to V2, and then you take the total weight of the path. So the sum over all edges in your path of YE, where YE is the edge weight, and we were assuming that the YEs are IID random variables. So graph distances would correspond again to all the y's being equal to 1. The nice thing about having them continuous is that actually the optimal path will be unique, and that will then also allow you to look at the properties of the path. For example, how many people were involved in spreading the rumor, the Chinese whisper problem, or the hop count problem. How many routers did the message pass through on its way from source to destination? And that's then a uniquely defined random variable. So I will be mainly doing this on the configuration model, but the problem on the complete graph has also been investigated in combinatorics. For example, this beautiful paper by Svante Jansson, 1, 2, 3 times log n over n for weighted complete graphs or something like that. And there's also a lot of interest in these kind of problems in theoretical physics, because it's related to order versus disorder, and they often think of strong disorder and weak disorder, and it's not always obvious what this means precisely, but the problem has been investigated quite a bit there as well. Okay, this is one of the main results in this area. So we look at a configuration model. We're assuming that the second moment of the degrees is finite and converges to a limiting degree distribution, and we assume a slightly stronger version where we have an extra logarithm in the moment. Now, remember that in the description of the neighborhoods in a configuration model as a branching process, we had size biasing. So you can also think of this as being the first moment of the size biased distribution, apart from a constant. And then this says that this size biased distribution satisfies an x log x condition. And this is something that is actually very important in branching processes, because it actually identifies precisely the phase where the martingale limit is strictly positive. So when the x log x condition is not satisfied, actually the martingale limit is almost surely equal to 0. And you have to renormalize in a slightly different way, Sinnette-Heide rescaling. So I don't want to be in that setting. I just want to be in the setting where if I look at the number of individuals in my branching process k away, I divide by nu to the power k, I'm actually converging to some almost sure limit, which is strictly positive on the event of survival. So that's basically what this guarantees. And in fact, uniformly in the parameter in the model, the size of the network. Then, if I look at the amount of time it takes for the rumor to spread, I have general IID continuous distributions for the edge weights. Then it turns out that if I look at the time it takes the rumor to spread between two random individuals, it's basically of the order log n times some constant which actually converges. And then this difference actually converges in distribution to some limiting random variable. So compared to the graph distances, there we also had that the graph distances were of the order log n times a specified constant, and if we were to take the difference, then this was a discrete random variable that somehow did not converge in distribution. Here we've made the problem slightly more continuous because of the continuous edge weights, and all of a sudden this weird behavior where you have tightness but non-convergence vanishes. This again shows that this really is a discrete discretization effect. So this is about the amount of time it takes the rumor to spread between two random individuals. Now, if you then look at the number of individuals involved in the shortest path, so how many people did the rumor pass through if it goes from the starting point to the end point, this turns out to satisfy a central limit theorem. So the number of edges involved is of the order log n, but then the fluctuations are of order the square root of that, the square root of log n. And if you look at this ratio, this actually converges in distribution to a limiting random variable, which is Gaussian. It's always Gaussian. So really a central limit theorem. So if you look at this picture, this sort of looks like a normal distribution. In fact, if we knew how large the graph was, And actually, this mean could also be thought of as being roughly proportional to the log of the size of the graph. And it turns out that if you look at the sample variance here, it's also proportional to the log of the size of the graph. In fact, even with prefactors 1. So if you think of this theorem, it's sort of very similar to what is happening there. So we can think of this as being a possible explanation for the effect that we see in Internet. Even though we don't understand that routing in Internet really has the same characteristics or the same behavior. Okay, I'm again writing here universality, and I'm writing universality there because somehow, irrespective of the precise edge weight distribution, if it's uniform or exponential or 1 plus uniform or sort of the absolute value of a Gaussian, or it doesn't matter. It will change these constants, but the universal behavior is always the same. You always get that the number of vertices involved in the shortest path is of the order log n and has a central limit theorem with a variance also of order log n. And it's also true that if I look at the amount of time it takes the rumor to spread from source to destination, this will be some constant times log n with fluctuations that converge in distribution. And in fact, even the shape of this limiting random variable is very alike for these different settings. It's not exactly the same, but it's always of a similar shape. Right. Now that was in the setting when the hubs somehow don't play a very prominent role. You have a finite second moment. So the largest degree is not too large. Now in the setting where tau is in between 2 and 3, it turns out that the process changes rather dramatically. We already saw that in the local weak convergence statement, in the sense that locally, your process looks like an infinite mean branching process. And now actually this infinite mean branching process, on all of the edges we associate an edge weight, which is an IID sequence. So that's a particular continuous time branching process, which is called an age-dependent process. And it turns out that in some of these cases, this age-dependent process explodes in finite time. And that means that in finite amount of time, in this model where you have an infinite number of individuals, in a finite amount of time, there will be infinitely many people who have heard the rumor. That is a very weird statement. Of course, in the graph, this cannot happen. But it can in the infinite setting. And you see that being reflected here by the statement that the amount of time it takes the message to spread from source to destination, that's going to be roughly independent of the graph size. So this limiting random variable, remember, here you have to subtract off something which tends to infinity. So the amount of time it takes a rumor to spread between source and destination grows when the graph becomes bigger, logarithmically in the graph size. Whereas here, it doesn't grow. It converges in distribution to a finite random variable, which is pretty weird. If you think about this, this is something like super efficient routing. Because the amount of time it takes you to send your email message to, let's say, the other side of the world is completely independent of the number of routers that are in your system. It's actually pretty nice. Okay? Now, this is not such a uniform statement. In fact, here I need to assume that the edge weights are exponential random variables. And that turns out to be crucial. In the case where these are IID exponential random variables, what we see is that the number of vertices involved in spreading the rumor again satisfies this nice central limit theorem. In fact, with the same prefactors here that are just functions of the power law exponent tau. So the number of individuals grows roughly like a constant times log n, and the amount of variability around it is again square root of log n, and even the variance constant is the same as the mean constant, which is weird. This here cannot always be true. So remember, in this theorem, it didn't make any difference in terms of, let's say, the general scaling behavior. It didn't make any difference what sort of a random variable I was taking. Whether it would be uniform or exponential or 1 plus uniform or, you know, anything was allowed, and you would always get a similar behavior. in this, it's obviously not the case because of a result that I've already shown you. So if I were to take the weights to be 1 plus an exponential, well, then my path at least needs to have length of the order log n. And actually, if I just take the shortest path, measured in terms of the graph distance, and sum out the edge weights, I will get something which is of that order of magnitude. So it cannot be the case that the best path actually involves more than log n vertices, because that would give a contradiction. So this logarithmic behavior of the number of vertices involved really cannot be true always, and nor can this convergence be true. So this weight, which I erroneously wrote as Wn here rather than Cn, as well as the hop count, they need to be at least of order the graph distance, which was tau2 log n divided by the absolute value of log tau minus 2. But in fact, in the case where these exponentials are, where these additional weights are exponential, they turn out to be, again, this 2 log n over log tau minus 2 plus a tight random variable, which is a bit of a weird statement. So we know that the shortest path satisfies this as well. It has the number of edges in it is 2 log n over the absolute value of log tau minus 2 plus a tight random variable. But now we're not only taking the shortest path, we also want our exponentials to be good along the way. If I just take the shortest path and my exponentials have mean 1, then actually the weight of this path is going to be twice as large. But what this says is you can actually find a path which basically has the same order of magnitude edges as the shortest path, but for which the sums of the exponentials along that path is actually also tight. So they become very, 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 very small, very quickly. That's pretty weird. So that not only says that there's a shortest path of that order of magnitude, but in fact there's many, many, many paths. And out of the very many, many, many paths of these order of magnitude steps, you can select one for which also the sum of exponential random variables along that path is very, very good. That's how this can be interpreted. Now we immediately see that in this setting it really depends a lot on the precise sort of microscopic properties of the edge weight distribution. If you take exponential, you get this nice convergence of the amount of time. If you take 1 plus an exponential, you no longer get that. So the precise details of the edge weight distribution matters. So we call this sometimes a non-universality result. Now it turns out that in these age-dependent branching processes, there are many more settings where you have explosion in finite time. So in the branching process, you spread the rumor to an infinite number of people in a finite amount of time. And this result certainly is still true in that setting. And that's sometimes called an explosive setting. So that's a more recent paper with a PhD student, Enrico Baroni, and Giulia Comiati. All right. So what is the bigger picture, the high-level overview? Well, first of all, we see that the random edge weights really have a marked effect on how the optimal flow occurs. Certainly in the case where you have infinite variance degrees, but also in the other cases, you really see that there is a big difference between the number of edges in the optimal path as well as the amount of time it takes, or the weight of the optimal path. One satisfies a central limit theorem with a variance that actually tends to infinity. The other is very much tight. Okay? As soon as the finite variance, the degrees have a finite variance, the behavior is relatively universal. That was the very first theorem that shows that you always have the central limit theorem, and you always have that if you look at the edge weight, the minimal weight, you subtract off the right constant times log n, but you get this convergence in distribution. So that's a pretty robust setting. And the proofs, well, I've already described that the neighborhoods in configuration model look a lot like branching processes. Here we put IID edge weights along the edges. In the branching process, I can do that as well. Now, if I do that, I get an age-dependent branching process. There's lots of theory about age-dependent branching processes, precisely of the type that I was indicating before. So, for example, there are results in terms of the exponential growth of the number of individuals at a given time t. And that's going to be related to the fact that the weight between two individuals grows like log n. Exponential growth means that the optimal weight is logarithmic. There's this inversion. And there's also something that is known rather generally about the structure of the trees. So, for example, if you have a tree of size n in such an age-dependent branching process, and you take a vertex uniformly at random out of the whole collection of individuals, actually the generation in which this will be is going to satisfy a central limit theorem. It's roughly going to be linear in the number of individuals, and the fluctuations are going to be of size square root. So that's closely related to the property that the number of individuals that the optimal path passes through satisfies a central limit theorem. In fact, one is a direct consequence of the other. All right. Any questions on this? All right. What I would like to do next is discuss a few consequences and related research. And I will do that much more briefly. Okay, so I already said this in words. Proof, coupling to age-dependent branching processes. There's two settings. Expectation d squared is finite. Exponential growth of the age-dependent branching process. Tau in between 2 and 3. Infinite variance for the degree distribution means infinite mean for the underlying discrete branching process. And then actually the continuous time branching process can be explosive. And these are the two settings. And then you really have to build up from there. So some related results. Of course, you can think about sort of other problems. So for example, in my open problem, I discussed something which is sometimes called the flooding. So suppose I take one vertex uniformly at random, but then I take the maximum time for the rumor to spread to the very last individual in my graph. So who's the person who will hear the rumor last? Right? And how long does that take? And for that, it's actually true that also this is logarithmic, but it's with a constant that is slightly larger than 1. And this you can also do for what is sometimes called the weight diameter. So suppose that I don't have one rumor in my graph, but everybody has its own unique rumor. What is then the last individual to hear all the rumors? That's what this is. And again, that's of the order log n in the case where you have exponential edge weights. And there's a constant involved. This is the typical constant. And there's a slight extra term that needs to be added. And that actually only depends on the minimum degree. It's most simple when the minimum degree is at least 3, then it's just 1 over the minimum degree. If the minimum degree is in between 1, it can also be 1 or 2. Then it's a bit more tricky to describe this extra little addition. Okay. Here are some results for the maximum number of individuals along the way. Right? So you can also maximize this Hn parameter. So Hn uv describes how many people are involved in transferring the rumor from source to destination, from u to v. And you can also maximize that over the final vertex. So that would actually correspond to who of the people would hear the rumor when it has come through the most number of individuals. So in terms of a rumor, this would be the least trustworthy rumor, the least trustworthy version of the rumor. Okay? And it turns out that, again, with exponential edge weights, and this is a nice result by Hamed Amini and Yuval, that again this grows like log n, and also the hop count diameter, if you were to do this maximizing over both vertices, again that grows like log n with a different constant. And you can analyze these constants on the random d-regular graph in terms of a certain function. And for this one, the function needs to be 0, and for this one, the function needs to be 1. And you can guess that this is the right thing by basically looking at extreme value theory. So the vertex here at the end is a rare vertex, so count the number of vertices for which the probability that the vertex is of that kind is of the order 1 over n. Now, if it's much smaller than 1 over n, then no such vertices are going to exist. If it's much larger than 1 over n, then at least the expected number of such vertices tend to infinity, and if you can control the second moment, you'll actually know that there's at least one such vertex. And actually both are of this kind, and it turns out to be described by the same function. Okay? So that maximal hop count. And there's also implications for other models. And this actually is a particularly nice one, which is again by Yuval and others. And that is all about the Erdős and Rényi random graph very close to criticality. So think about G and P, where P depends on n. And it's now 1 over n plus a little bit. But it's 1 over n plus a little bit in such a way that there's still one unique largest component, and its size is roughly deterministic. So we know that we know what its size is like, and what they've been able to do is to describe the entire topology of this object in terms of a first passage percolation problem on a configuration model. And basically the idea is that if you're slightly supercritical, the giant component, the maximal component, is going to be deterministic roughly in size, and it's going to have many cycles. Cycles are building up immediately after the critical point. And you know roughly how many there are. Now suppose we construct a graph from our nearly critical Erdős and Rényi random graph by just removing all of the stuff that is not part of a cycle. Okay? That's sometimes called the two-core. So you basically cut off all the trees that are hanging, that are the ones that are connected to the cycle. And now this is a graph. It's a graph that is a union of cycles. And now contract all of the long paths that may be in there, contract them to a single edge. That gives you the kernel. And it turns out that you can prove that this kernel is very closely related to a configuration model. And if you're very close to the critical value, yet still barely supercritical, it turns out that this optimal structure basically only has vertices of degree 3 in it. That's quite nice. And also, the length of the edges, which I was contracting, turns out to be very closely related to a geometric with a very small parameter, a very small success parameter. Now, a geometric with a very small success parameter scales like an exponential. So if we would forget this difference between it being discrete and continuous and just say that it's exponential, what we would be getting is precisely first passage percolation on a configuration model. And they've been able to use this in order to determine the diameter of a slightly supercritical Erdős and Rényi random graph by linking it to a first passage percolation problem, which I think is a very interesting result. Okay. Now there's another problem that I've been interested in quite a bit, and that's a competition problem. So rather than thinking about sort of rumors spreading from source to destination, I think about two competing species that are located at two different vertices, and they try to explore the graph. Think, for example, about viral marketing. There are two types of products. They start somewhere, and they want to, through, let's say, communication to your friends, they want the product to spread. So think about either a Microsoft operating system laptop or a Mac, right? Something like that. And once you've made up your mind, you've actually bought this particular computer, well, you're actually not going to change your mind very quickly because these things are relatively expensive. Okay? Very simple model. It's related to rumor spread because as long as the competitions don't see each other yet, it's precisely a rumor spread. But when they start seeing each other, they're actually competing for the same territory, so they're blocking each other, which actually makes the process quite a bit more difficult. And there's something that is quite surprising. So if you're on a configuration model with infinite variance degrees, it turns out that even when the two rumors spread at different rates, so when I say rates, it means that the traversal times are actually exponential, but these exponential random variables might have a different mean. And you would somehow think that if you have a smaller mean, that you're ahead in the game, and you're probably more likely to actually grab the majority of the market. Well, that may be true up to a certain extent, but it actually turns out to be the case that irrespective of the two parameters that you choose, the slowest species can still grab the majority of the market. And when it does so, the faster species will only have a bounded number of vertices that actually converges in distribution. So it's a very unequal game in a certain sense, and that's why we call it the winner takes it all. And this is written together with a Swedish mathematician, so I think the winner takes it all is, it's taken from the ABBA song. The winner takes it all, the loser standing small. Very literally true. So what we can show is that irrespective of the precise speeds, of course the probabilities are going to change, but each of the two species can grab the majority of the market and then basically have the entire market except for a finite number of points with positive probability. And the probability, of course, depends on the speeds. Right? If you have a faster speed, the probability of you winning will be larger, but there's still this off chance, which happens with positive probability, of the entire market being grabbed by the other species. And you know, if you want to compare this to, let's say, real estate marketing, they always say that there's three important issues when you want to sell your house. Location, location, location. It's precisely the same thing here. It really is the local surrounding of your starting point that can give you the head start. If you're somehow located very positively, for example, in a vertex that has extremely high degree, you'll rush off very quickly, and then you'll be in business, and you actually grab the majority of the market, even though you, edge-wise, might be a little slower than the other guy. Okay, so that's the picture. And there's a lot of other work that I'm referring to here for passage percolation as a competition model on random regular graphs. We have an extension of this competition process when you do it with equal weights. That's, of course, rather dramatically different. So if you think about sort of this as a rumor spreading game, it would be the graph distance rumor spreading game. And actually there it turns out that the fastest species always wins with probability going to 1. So there it really helps to have an edge on your competitors. But when they have equal speed, there's still two things that can happen. Either you both grab a positive proportion of the market, we call that coexistence, or one of the two species actually gets the majority. And actually, in terms of sort of graph distances, if you think about it, if you think about growing these competitions, we know that the high degree vertices are very important. And actually, we can show that the species that gets to the highest degree individuals first is the species that wins. But they might actually get there at the same time. That's when you get coexistence. Okay. And so we did this first in the infinite variance case. In the finite variance case, exponential edge weights, there is also an extension to this. And there again, the speed is tremendously important. If your speed is slightly higher, you will get the majority of the market, and the other person will get very little. And again, you have competition when there's a possible coexistence when the two species have the same time. In a certain sense, that's a slightly less surprising result. This is what you would believe to be true. But the proof is relatively beautiful, I think. And it really does things by connecting up the process of exploring the graph as a Polya-Ern. And then you can show these kind of results that I was describing before, that somehow ratios converge to almost sure limits. You can use that, and that result will imply that the proportion of individuals that is captured by one type or the other type will actually converge in distribution to a continuous random variable. So they really get a positive proportion, a random proportion of the total graph. So it's a nice result and a nice proof as well. Okay, I'm almost done. Let's skip this. Conclusion on routing on the configuration model. There are many results on first passage percolation on random graphs, yet there's many things that we don't know yet. The setting where you have finite variance degrees we understand relatively well, and the situation is relatively robust. relatively universal. In the setting where you have infinite variance degrees, it's much more subtle. And one of the ways how you can understand why this is much more subtle is that there is a big distinction in terms of the topology between the setting where you have finite variance degrees and you have infinite variance degrees. So in the finite variance degrees, basically the largest clique that is going to be embedded in your graph is a triangle. And that is only going to happen with positive probability, not even with probability converging to 1. So if there's no triangle, then the largest clique you have is a 2 clique, which is an edge. They certainly you will have. Right? So that's the setting with finite variance degrees. Very small cliques. In the infinite variance setting, toying between 2 and 3, it turns out that with high probability there's a clique that has size a positive power of n. And that means that if you're going to be doing first passage percolation on this graph, well, you better understand to some extent what first passage percolation on a large clique looks like. Now, a large clique is a complete graph. And actually, we don't really understand the complete graph very well. Surprise to me, number one. Normally, you understand the complete graph very well, and then you make the excursion to the random graph. Life becomes much more difficult, much more technical, etc., etc. And very often, in the end, we're able to sort of pull the result off. Here, it's quite different. We understand the random graph relatively well, and we don't understand the complete graph at all. We really don't understand it at all. There's one case that we do understand. This is the result by Svante Jansson, where you take exponential edge weights. This is this 1, 2, 3 times log n over n result. So if you look at the amount of time it takes you to spread the rumor from I to j, of course this random variable is not going to depend on I nor j. It's a complete graph, so that's very easy. That's going to be over the order log n over n. And for a typical pair, it's going to be like 1. For a typical I, but maximally over j, it's going to be 2 log n over n. And for maximized over I and j, it's going to be 3 log n over n. That's a very nice result. Now, in his paper, actually, Svante proves quite a bit more along the lines of the kind of things that I've been discussing today, namely fluctuation results. So if I multiply Cn by n and subtract off log n, in the first setting, it converges to a funny random variable that is a sum of 2 gumballs minus a third. In the second case, again, I subtract off 2 times log n. It converges to a sum of 2 gumballs. And in the third case, he wasn't able to show the convergence. And in a later paper with Shankar Bhamidi, which appeared just this year, we managed to show that, again, if you take this maximum and subtract off now 3 times log n, then this converges to some random variable that is actually fairly tricky. It's a very complicated object. And it's closely related to a diameter in a slightly supercritical Erdős and Rényi random graph. OK. Now, this is for exponential edge weights. And exponentials are very special in this first passage percolation business, because it basically, in an exponential setting, somehow the evolution of the graph process, how it grows, is Markovian. That's actually very nice. And that's not true for any other random variables. And in fact, we have quite a few examples where we can investigate what this object is. You know, it can be basically anything. 1 over the square root of n and basically completely deterministic. It can be much larger. In fact, we believe that there's a whole class of random variables, IID random variables, for which this time is closely related to the minimal spanning tree problem. So that's sometimes called infinite disorder. And there's lots of things that, there's a few things that we know, and there's lots of things that we don't know for the complete graph, which I found a surprise. OK, so there is a relation to the minimal spanning tree on the complete graph as well. All right. I would say that in general, in these first passage percolation problems, there's still many things that we don't know. It's a gold mine, I think, of pretty interesting problems. If you want to know sort of the major sources of inspiration that have gone into this, this course, there's, I think, 5 slides on references. These are on my webpage, so you can just look them up from there. Here are some papers about the configuration model. Oh. in homogeneous random graph, including the very big paper by Bolobas, Janssen, and Reardon of about 120 pages, studying inhomogeneous random graphs in an enormous generality. It's a very powerful methodology and a very powerful paper. Preferential attachment model, of course, Barabasi and Albert. The Bela and Oliver paper about diameter, the degree distribution, etc. And then there's still something about first passage percolation and flows, including the very recent scaling limit paper of the minimal spanning tree on the complete graph, which I think is a beautiful piece of work, linking the minimal spanning tree on the complete graph in a very detailed way to critical percolation on the same complete graph, so the Erdős and Rényi random graph. It's really a very beautiful paper. All right, thank you very much.